What we're going to do in this Minitab session is we want to convince you of the validity of sampling as compared to this process that many of you are more familiar with, where you're analyzing the whole population. And what I need to be able to do is to show you exactly how we're going to take a look at data in Six Sigma. We will use sampling very, very effectively. So what we're going to do is we're going to start with a Minitab worksheet that I've created. Column 1 is going to be the whole population. You'll see there's thousands of rows. Then we'll take a sample from Minitab using random sample from the columns of 960 in column 2. Then we took 480 column 3, 240, 120, 60, 30, and 15. And what we're going to do with each of those columns is we're going to compare the sample data against the population. And we're going to ask two questions. Is the mean any different from the population? And is the variance any different than the population? So let's take a look at Minitab, and the data file set is going to be called Sample Me. And so let's take a look and say, what do we actually have here? So to understand what's in the population, we go to Stat, Basic Statistics, and Graphical Summary. Okay, and I click on Graphical Summary, and let's just double click on Population. Okay, and now we just click OK. And what we see here is the result of the data. So here is the population. This is real world data. And we can see the distribution. It's not really quite normal, okay? So we'll see the p-value here is less than 0.005. And so that says it's not a normal distribution. That's based on the Anderson-Darling normality test. And we see that there's this long tail. We can see it coming off here to the right, and the data gets further and further. The mean is 6, so it's right here in the center. Yet we can see that this data comes well off to the side here, okay? So this is the data, and so the mean is out here, but the median, or the 50th percentile, is way over here. So the median is 5.4. So we see that the data is skewed. It's got a tail going to the right. So as we're taking a look at this, one of the questions is, if we sample the data, will it actually still have the same distribution? And is this sample equal to the population? Okay, so now I'm going to make that smaller. And so what I see here is I have this population, and actually let me take one more look at this window, and we say, okay, this is the summary report. And I wanted to show you also the sample size. So the sample size is 10,000 data items. So I've already sampled this from some real world data, which is performance data. It's a reliability data, actually. And so I'm not really surprised to see this type of distribution out there. But it's 10,000 items of real-world data. Okay. So the question is, if I take a sample from this data, how representative is that of the original data? Okay. Now, the first thing we have to do is see, how do we take a sample in Minitab? So we come down here under Calc, and we see Random Data, and we sample from the column. So this is how I built this up. Now, the reason I'm not going to walk you through this, and I want you to start with data I have, is every one of your Minitabs has a different random number generator. And so the random number generator will sample differently for each of your different Minitab applications, because it then pulls this out of a random access sheet. So rather than having you do this analysis with totally different data on everybody's computer, which might get a little confusing, I decided that what I do is fix this, but I want to show you how the sampling works. So if we click on Sample from the columns, we say, how many do I want to select? So let's just say I want to select 10 samples, because I'm going to use a different number. Sample from population, and store it in where? Well, I'm going to store it in C10 so I don't get, or C12, so I don't get confused, okay? I don't want to click Sample with Replacement, because if I click Sample with Replacement, it takes the sample and then it will put the sample back in, and I could actually bring that sample out 2 times. Now that actually shifts the distribution, and we don't really want to talk about that. That's more of a black belt level of thinking about the process. So we don't want to click the box. That's the thing we have to remember as green belts, okay? And then we click OK, and there it gave me those numbers. Okay, so if I take a look at those and I say, okay, let's now go back to Stat, Basic Stat, Basic Stat. You have to be very careful with this and keep the mouse on this careful. and I see column C12, okay, I take a look at this, what I see is, this shift somewhat slightly, okay, and it's a small distribution. So this is telling me I probably don't want to use this, okay, but I'm going to tell you, what I don't want to do is say sample size of 10 out of 10,000 is an adequate sample size. So the question is, at what point in time does sample size actually degrade where it no longer reflects what the underlying distribution was? So how do I test this? Well, one way to test this is to say, let's compare the means. So the way to compare the means is to go to stat, and then we have basic statistics, and I have a two-sample t-test. Okay, and I have the samples are in different columns, so I selected his. Each has its own column. So sample 1 is population, and sample 2 is C12. Okay, and for graphs, I want to see the box plots. Okay, so I click on box plots, and I click OK, and now I'm just going to click OK. And what I see is that here is this interesting graph. It says the p-value is 0.0056. So that says there's no statistical difference even with that sample size. Whoa, that's surprising. What that means is that if I was to draw a statistical summary based on the sample size of C12, it would reflect the whole population of 10,000. Wow, that's interesting. But look, it's so much longer here. Is the variation the same? Well, we can answer that question if we go back to stat, basic stat, and now stat, I'm getting so excited here I can't stay on this thing. Basic stat, come over slowly, 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 and two variances. Okay, so we see that they're in different columns. So each is in its own column. Population is one, and C12 is the other. And we click then OK. Okay, too few items. Okay. And so it says you can't do that because there are only 10. So Minitab won't calculate with 10. Okay, so there's a problem. Okay. Oh, the problem is Greg didn't click on the right column. Okay, C12. Okay, so Minitab does calculate it. And what we see is, as we expand this here, there are two different tests. And so if we take a look at them, neither of them is below 0.05. And we take a look at the variance, and we see they're basically equal. Now look, all of that, and there was just this one data point way out here, I think. So as I'm looking at those things, it says basically there's no difference in the amount of variation, even with that small sample size. Whoa, Greg, didn't you just tell us that that's not a good sample size? Well, I did. But randomly speaking, I can come up with actually a good sample with random data draws. So that's with a sample size of 10. Well, let's come back and start taking a look at these other samples that we have. Okay, so here we have sample of 1,000. And we can just get into a pattern of how we click. So the first thing I want to do is take a look at the graph. And so I go to stat, basic stat, graphical summary. And now I'm going to take a look at sample of 1,000. And I click OK. And there it is. And it's no longer, now it's clearly looking at the same shape, 5.4 versus 6.2. And so I'm looking at very similar types of things that I had before, but they're not quite the same. So are they statistically different? So we can go to stat, basic stat, two-sample t-test, and compare. Now, no longer populate, it is population, but it's no longer C12, it's going to be sample 1,000. And the graphs will stay the same as the box plot, so we don't have to change that. Whenever you're in a Minitab session and once you select something, you can repeat it without having to go do those keys all over again. And we see two things. Now I'm going to just move this off to the side here. And we see that there is a statistically significant difference here. This is interesting. So the p-value is 0.018, okay? And it says that there is a statistically significant difference. And I'm a little surprised at that. But as we take a look at this graph here, we see that the bulk of the data, it's a flat line. And the flat line is saying that there's really not very much difference. But because the data sample is so big, that the amount of distribution we have is so small, that differences will show up even when differences do not actually matter. So we don't get reliable data when we're dealing with this. So if I go back and take a look at the variance then, so I go stat, basic stat, and I take a look at the two variances. Now instead of C12, what I'm going to do is put in 1,000 and click OK. And here we see, again, the p-value is 0.124 or 0.097. So this first test is for normal data. This data is not normal. So it says for not normal data, it's significant. Okay. Well, should it really be significant? Not really, because what we see is that this data is actually from the same database. So let's go down and start taking a look. So this says high data sampling rates are not necessarily going to be reflective of the population. So let's take a look then, and we will edit the last, or excuse me, we won't. We will take a look at the next sample size. So we'll take a look at graphical summary. Now let's take a look at for 125, okay? And at 125, we see, okay, the mean is 6, and the median is 5.5. Let's take a look then at stat basic stat 2 sample t-test. So it's population versus 125. And we see that they look the same, and there is statistically no difference, 0.905. If we take a look at the stat basic stat 2 variances, and the sample size of 125 again. Oops. And we see there is no difference with the p-values above 0.05. That's interesting. So the smaller data is actually representing the data much better than a larger data set was. Now, I have to tell you that larger data set was probably a random excursion. It was the way the sampling was done. But let's take a look now at a different one. Let's go stat, and instead of this, let's take a look at 30. Okay. Now remember 30 we talked about because that's an interesting one. So here's the mean is 6.2 and the median is also 6.2. Okay, so this is saying that they're almost like a normal distribution. Except as we see this shape, it doesn't quite look normal. And so let's take a look and say, is that statistically significant in terms of difference? So again, we go to stat, basic stat, and 2 sample t-test. And again, we're going to take a look at 30. And we take a look and we say, nope, there's no statistical significant difference. Okay, how about in the distribution? Stat, basic stat, 2 variance test. And again, it was sample size of 30. And we see again, there's no statistically significant difference. So what I hope this illustration has shown to you is that sampling doesn't hurt you. Sometimes when you're dealing with large data, it does hurt you. Because as you're taking a look at this, you can get some variances that actually don't really matter much. Because the difference to detect has become so small as you're taking a look at this. So again, if I want to understand what's happening here, I can take a look at stat, power and sample size. And this is the 2 sample t-test, for instance. So my sample size I might get, and I'm going to say, okay, what happens if it's 30? The difference to detect is a 1.0, okay? And I know that this, I got that wrong one in there. The standard deviation is again 1.0. So I have to remember to use not points, but use the commas. And if I take a look at this, so at 30, the sample size for this, it says the power to detect is 0.96, which means the risk to the customer is 0.4. So we're balancing then, if you will, the risk to the customer, the beta risk, and the alpha risk, the risk to the company, in terms of the sample size of 30. And that's one of the things we would like to be able to do. So again, keep in mind, if you have to come up with a sample size, you don't have any real information about what it is, and you need to have a number, and you just are sort of bringing it out of the back of your head or pulling it out of your sleeve or some other place in your anatomy, you can always use a sample size of 30, and you're going to be pretty safe in terms of having an adequate representation of the risk to the company as well as the risk to the customer. Now that we've done this, hopefully we've convinced you that it's okay to sample much smaller data sets rather than the complete set. This gives us actually a couple of advantages. If we take a look at the overall data set and we can identify rational subgroups within there, now we can take a look at those rational subgroups using the smaller sample and compare to the overall performance. And see, are there factors in those small sample sizes that make a difference compared to the overall performance that we see for the process? This can help us to identify those circumstances where we have a best of the best situation or a worst of the worst, Bob and wow. So again, as we're looking at this sampling, this is going to be one of those ways we can identify which rational subgroups are the most important for further analysis.